We recently looked at gradients of vector-valued functions, and we learned how to take derivatives of vectors of functions with respect to other vectors. This video is going to seem a little strange because we're going to learn how to take gradients of vectors with respect to matrices. So what does that even mean, and how do you do that? Well, let's start off with kind of a somewhat numerical example. We'll say that A is a 2x3 matrix. It contains these 6 components here. Just notice they're labeled according to row column. So little a11 is the first row, first column entry in that matrix, all the way down to a23. And by writing it this way, this just means A is an element of real numbers, 2x3 real numbers, or 2x3 matrices that consist of real numbers. And X is a 3x1 that lives in R3, and that contains these 3 variables, x1, x2, x3. We're going to define our function as we have before, where the function is going to be the matrix times X. Now we're going to get a vector of functions from this, because when we take X and we multiply this, we'll get a function in the first row, which, if you notice, when we multiply these two, this component times the first column plus this component times the second column plus this component times the third column, we will get a11 times x1 plus a12 times x2 plus a13 times x3. It's writing it in scalar form for just the first row. So x1 scales the first column, which means it scales all of the elements in the first row. x1, x2, and x3 do. And then x1 will multiply a21. It'll multiply, x2 will multiply a22. And x3 will multiply a23. So this is what we would get. And we denote what's in the first row. Notice this is just one value right here. These 3 things are being added together. And so this formulates what we call f1. Then the bottom row, no vector. That's just a scalar now. It's the function f1, and the bottom row is the function f2. So when we compute, the question is, well, how do we compute the derivative of this vector of functions, f1 and f2, with respect to the matrix A? Well, in a nutshell, the way we do this is we define this to mean that we want the derivative of each function, fi, where in our case I can be 1 or 2, with respect to each component of A. So basically we want the derivative of f1 with respect to a11, the derivative of f1 with respect to a12, derivative of f1, so with respect to all 6 of these quantities. So it to try to write it out in terms of, well, what is the derivative of f1 with respect to A? Well, that itself is going to create a matrix of values. In fact, it's going to be a 2x3 matrix of values. f1 is one function. That's this guy, this top row here. I'll go ahead and do this in a different color. So we want to take the derivative of this. That's going to be our first row. Our first row will be the derivative of this with respect to each of the elements of A. So in other words, what this will have in it is this will have the derivative of f1 with respect to a11, and then the derivative of f1 with respect to a12. So notice all we're doing is we're just going across the first row of A and taking the derivative of f1 with respect to each of those entries. And now in the second row, we're still focusing on f1, but now we're going to take the derivative of f1 with respect to a21, and then the derivative of f1 with respect to a22, and then the derivative of f1 with respect to a23. Now, the reason I've labeled these instead of putting numbers in them is because it's kind of weird to think, if this were just a constant like 5, take the derivative of f1 with respect to the constant 5 may seem kind of like a strange thing to do. So I'm just leaving these elements labeled this way. Well, let's now ask ourselves, what would be the derivative of this entire function with respect to thinking about A11 as a variable? Well, that means that all of the other quantities in this expression are constant. So the derivative of this entire function with respect to just A11, well, the derivative of x1 A11, x1 times A11, I'm going to write it like that because we're thinking about this as the variable of differentiation here. And so think about x1 as a constant with respect to A11. The derivative of x1 A11 with respect to A11 will just be x1. Okay? And then the derivative of this, because that doesn't have an A11 in it, that's thought of as just a constant with respect to A11, it'll be 0. And the derivative of this with respect to A11 will also be 0. And that's just this first bit. So it'd be x1 plus 0 plus 0. Now, let's go back to the function f1 and take the derivative with respect to a12. Well, the derivative of this term, this doesn't have any a12's in it, so it's 0. It's a constant. The derivative of this with respect to a12 will just be x2. And the derivative of this with respect to a12 will be 0. So our answer for what's the derivative of this entire thing with respect to a12, well, it's just x2. That's the only term that depends on a12. Now we do the same thing, derivative of that same function with respect to a13. Well, again, the only term that has an a13 in it is this last term, and the derivative of that with respect to a13 is just the constant x3. Remember, we're treating our members of A as the variables, and what we would normally think of as the variables are constant here. We're not differentiating with respect to x1, x2, x3 like we did. We're differentiating with respect to the matrix A. Now we would move on. We'd say, okay, well, what's the derivative of f1, this thing here that's in orange, with respect to a21? Well, this expression for f1 doesn't have any a21's in it. So the derivative of each of these terms with respect to a21 will be 0. f1, this boxed-in function with respect to a22, again, it doesn't have any a22's in it, so all of these terms have a rate of change of 0 with respect to a22. And finally, with respect to a23, also 0. So the way we might often write this in more compact form is this is x vector transposed, right? If x is the column vector x1, x2, x3, then remember that the transpose of a matrix or a vector is basically each of the vectors, column vectors, turned into row vectors. So this would be x1, x2, x3. And that's why we could just say that that row is the transpose of the x vector. This right here is the 0 vector, but when we say the 0 vector, it's a column of zeros. So we actually, what we have in that row is the transpose of that 0 vector. And the transpose of the 0 vector is just 0, 0, 0 as a row. So this is the 0 vector transpose. Notice that this one derivative for f1 with respect to A is a 2 by 3. Now, to get the derivative of the next function with respect to A, we have to go through a similar process, except now this would be f2, except all of these derivatives will be with respect to, will be the derivative of f2 with respect to each of the members of A. So now we're focusing on this second function, f2, and we want the derivative of f2 with respect to a11, with respect to a12, with respect to a13, with respect to a21, with respect to a22, and a23. Sorry, I forgot my partial operator there. Now this is going to produce a very similar result, except notice that function 2 does not depend on a11, a12, nor does it depend on a13. So the derivative of this entire purple expression with respect to a11, a12, and a13 will be 0. And now the derivative of f2 with respect to a21, well, that does have an a21 in it, but only in the first term. So the derivative of a21 with respect to a21 is 1, but then we have this constant x1. And similarly, for the derivative of that function with respect to a22, it'll just give us the coefficient of a22, which is x2, and really for that last term. So notice that we get another 2 by 3 vector here, and this one we could write as the 0 vector transposed in the top row, and then the x vector transposed in the bottom row. So there's 2 functions, each of which has its derivative resulting in a 2 by 3 matrix. So the question is, well, how do we write this? Well, there's a couple of ways. One way is to think of this as two 2 by 3 matrices, excuse me. And the two by 3 matrices could be thought of as a 2 by 2 by 3. That's called a multi-dimensional array. And in mathematics and computer science, it's often referred to as a tensor. So, okay, well, that means that to represent it as a 2 by 2 by 3, let's think about it this way for a moment. So we know that df1 dA will produce a 2 by 3 array. So I'm going to represent it like this for a moment. And df2 with respect to A will produce another 2 by 3 matrix. So what I can go ahead and do is I can think about this first matrix right here, and I can think about this second matrix right here. So this guy we'll call df1 dA. This guy we'll call df2 dA. And I can sort of think about this as having two 2 by 3 components. And so as a result, I can think about the first one as a 2 by 3 sort of 2 by 3, I'm going to say this, like a set of blocks, right? So this is a 2 by 3, and this is a one-dimensional extension, right? Because it's technically a 1 by 2 by 3. 1 by 2 by 3. It's just 1 2 by 3, and this is just a 1 2 by 3. So that means if I put the other one back here, and I stacked it like this, now I have not a 1 by 2 by 3, but I have a 2 by 2 by 3. And that's what we're talking about for a multi-dimensional array. We just sort of stack each instance of a 2 by 3 and represent it that way. Now you could also, sometimes what you do to represent this in a more usable format is reshape it. Sometimes this process is called flattening. And one way to do this would be to take our first 2 by 3 and then our second 2 by 3 and stack them this way, for instance. And now we get a 4 by 3. And that results in a flattening because now we sort of flatten from a three-dimensional array into just a two-dimensional array. So there's a couple ways to do that at least. But hopefully this helps us better visualize what we're doing. And in general, A may just be an m by n matrix, right? So A will be m by n. And here again, we could label those components A11 all the way up to A1n. And then downwards, this will be the mth row, first column, all the way over to the mth row, nth column. And there is our representation of that matrix. And x, the vector x, is just going to contain x1 all the way down to xn. Now, when you multiply these together, for our function, a times x, you will get a11 x1 plus a12 x2 all the way up to a1n xn. Okay, that's this component times this column all the way over to this component times this column. And that means that working down, the last row will just be a m1 x1 plus a m2 x2 all the way across to a mn xn. And so you can imagine that depending on which component of the matrix you're taking a derivative with respect to. So think about this as f1 all the way down to, this is the mth function. So similar for like a 2x3, we just went from f1 to f2 though. And now, how do you take the derivative of f1 with respect to a? Well, again, that just means taking the derivative of that first row, can do that in a different color, take the derivative of this thing right here with respect to each of these components. Well, in the first row of f1, f1 depends on all of the elements of a within that first row. So the derivative of this entire expression with respect to a11 will be x1. And the derivative of this entire expression with respect to a12 will just give me x2. And basically the derivative of this first row with respect to all of these elements in the first row of a will just give me back the elements of this vector x, which notice is simply the x vector transposed. Now, as we work to the next row, a21, a22, all the way up to a2n, this doesn't have any of those a's in it. So this will return just a bunch of zeros. And that will be true for every row after that. Only the row has the elements consisting of what elements are in our current f. Only those will return the values of x. All of the other return rows will return 0. So how big will this be? Well, this will be m by n. So for each function, we're going to get an m by n matrix. And for df2a, the first row will all be zeros, because notice that the second row, which will be a21, x1, a22, x2, it doesn't have a11 through a1n in it. The only elements that it has is a21, a22, all the way up to a2n. So this will, in the second row, return x1, x2, all the way up to xn, and then 0, 0, 0, and then zeros all the way down. So this will return the 0 vector transposed, the x vector transposed, all the way down to the 0 vector transposed. And this will repeat itself. So basically each function down the list up until the mth function, that one will have zeros everywhere. Until that very last row, because fm has all of the bottom elements of a in it, am1, am2, amn. So in this case, the bottom row will return x1 through xn, and that one will have a bunch of 0 rows up until the last row, which will be the transpose of the x vector. So each of these, notice, will be m by n. And how many of them do we have? Well, we have m of them. So we'll have m n by n matrices. And therefore, the derivative of our vector of functions with respect to the A matrix will be an m by n matrix. M functions, each of which will have m by n derivatives with respect to A.